Section 3 from Unit 3 talks about electron configurations. Electrons are not arranged randomly in an atom. They kind of exist in layers that we call shells. So if we think of it as this being the nucleus here, and outside of that, okay, we have these kind of shells that develop. All right. Now, if you go on and study more chemistry, you'll learn that, okay, it doesn't exactly look like this. But for the purposes of learning how the electrons work inside of atoms, this is how we're going to learn it. Okay. But each one of these layers we call a shell, and each shell can hold a certain number of electrons. This first shell can hold a maximum of 2, and then 8, and then 8, and then it turns out that 8's really the maximum that we can get out here. So every successive one has a maximum of 8. Okay. Valence electrons. So as these things begin to fill in for an atom, the valence electrons are the electrons in the outermost shell, whether that's the first shell, the second shell, third shell, whatever it might be. It's the ones that are in the outermost shell. Okay. In bonding, valence electrons are very important. It's because the electrons that are furthest away from the nucleus are the ones that are going to bond to another atom. So as another atom would approach to form a compound, the outermost electrons are what actually interact, not the innermost. Okay, so if there's electrons out here, these inner ones are not interacting with this other atom. The ones furthest away would be. When atoms gain or lose valence electrons, they form ions. Okay, so remember, these are negatively charged things, so we could add things into these shells or remove electrons out of these shells, and that's going to change the charge here, since I would no longer have an equal number of protons and electrons. So when I change the number of electrons in a neutral atom, okay, I create an ion. An ion is simply an atom that has gained a charge. Okay, so how many valence electrons does an atom have? So it's actually really simple to do. Remember earlier when we were talking about groups and A groups being the main group elements? Well, anything that's in an A group, all you need to know is the group number, and that will tell you how many valence electrons that particular element has. So let's take a look. We've gone ahead and copied the periodic table onto here. Carbon, it's right here. It's in family 4A. It has 4 valence electrons. Super easy. Nitrogen, family 5A. It's going to have 5 valence electrons. We'll do one over here. Potassium, family 1A, is going to have 1 valence electron. Okay, so why don't you try to do these other 3 right now using your periodic table. Okay, so you should have gotten 7 for fluorine, 2 for calcium, and 8 for neon. So hopefully you got that. The next question is, now how are they arranged in the shells? So how does this actually happen? As you can kind of guess here, the family numbers, okay, at least for group A elements, tell us the number of valence electrons, which is really helpful, which means everything in the same family has the same number of valence electrons. So how does that happen? Now we need to look at that. Okay, as we said a few minutes ago, the first shell only has a maximum of 2 electrons, okay? And then shells after that will have a maximum of 8, at least for our purposes right now, trying to understand this. Okay, so hydrogen has 1 proton and 1 electron. That first electron is going to go in the first shell. Okay, so that's where it goes. Helium has 2 protons and has 2 electrons. So those 2 electrons will go into the first shell. Lithium has 3 protons and 3 electrons. The problem is that it's got 3 electrons and the first shell only holds 2. So the first 2 go into the first shell, and then the third electron goes into a new shell, which now the one that's it's currently in has a max of 8 electrons total. So it could accept up to 7 more. Okay, it's probably not going to do that, but it's possible, okay, that it could at least fill that spot in. And if you look at it, right, hydrogen is in family 1A, and lithium is in family 1A, and they both have 1 valence electron, right? And since the group number of A families tells us the valence electron, well, that's what we got here. There's 1 electron in the outermost shell of hydrogen. There is no extra shell. There's just 1 shell. Lithium has 1 electron in the outermost shell. These other 2 are not outermost electrons. Okay, so it's got 1 valence electron. So hopefully you can see that pattern starting to form there. Okay, so why do elements form ions? Why do they form charges? Why do they actually want to react? Why do most of them actually turn into compounds, form compounds, instead of staying as pure elements? The reason is, in general, atoms want to have the same electron configuration as the nearest noble gas to it. Okay, so take for instance here sodium. Okay, it's got an atomic number of 11, and it's got one valence electron. Okay, it's in family 1A. All right, so it's got this outermost electron here. Okay, and remember the noble gas elements are the ones over in family 8A, so they're all the way over on the right side of the table. So we're looking all the way over here. Okay, those are family 8A. What it's trying to do, what sodium wants to do, is have a completely filled outermost shell. If you notice, everything over in family 8A has a completely filled outermost shell. That's why they don't react. Okay, they're called noble gases because they don't react. So neon has 10 electrons, right? It's number 10, it's right there. The first two go in the innermost shell, the next 8 fill the second shell. Remember we said 8 was the maximum for every shell after the first one there, which only had a maximum of 2. So no more electrons can go into that shell, so neon is not going to react. Sodium is element 11. It's got one more electron than neon does. And so what it's going to do is it wants to get to have the same setup of electrons as the closest noble gas. Well, sodium's right there. Okay, neon's right there. It's going to want to lose an electron to make that happen. There's two ways that sodium can get a completely filled valence shell. It can add 7 more electrons into this thing, right? 1, 2, 3, 4, 5, 6, 7. All right. Or what it can do, all right, is come in here with a white marker, okay? Or what it can do is it can just remove that outermost electron, and now all of a sudden it's got a completely filled outermost shell. Now it's only got, when we do this, 10, whoops, make the marker a little thinner there. It's only got 10 electrons now, and it's got 11 protons, which means it has an overall +1 charge. So that's why things here in family 1A, we said earlier when we were talking about the alkali metals, that they tend to form +1 charges. And that's the reason. That outermost valence electron tends to fall off so that sodium can have the exact same electron setup as neon. Okay, and everything else in this family is going to do a similar thing because it's got one valence electron that it's going to want to lose. Okay, so that's how we end up with a +1 charge on sodium and things in the 1A family. Okay, so now let's think about what sort of charge is fluorine likely to produce. It's an element with atomic number 9, all right? And again, still wants to have the same number of electrons as the nearest noble gas, okay? So what's going to happen here? Well, let's think about it. So it's got 9 total. It's got 2 in the innermost shell and 7 in the next shell out here. And it wants to become like neon, which is the closest noble gas, right? This has 9, this has 10, okay? So it's going to want to become like neon. Well, neon's got 10 electrons. Fluorine's going to want to get a completely filled valence shell. It can either add 1 electron, right? Or it could simply remove, change the marker here, okay? It could remove this entire outermost shell, which would also give me a completely filled valence shell. The problem is now it's only got 2 electrons. So in terms of things likely to happen, it's more likely that we're going to add 1 electron here to get a completely filled shell than to lose 7 of them. Okay, you have a huge charge imbalance, or 9 protons and 2 electrons. Here we have 9 protons and 10 electrons. So let's go ahead and also just write down those numbers here. So now we end up with 9 protons and 10 electrons. This atom has gained an electron, okay? It's now got 1 extra electron, which means its overall charge is -1. And so if we stop there and think about that, go back to fluorine, it's part of the halogen family, which we talked about. All right, halogens, I told you then, had a tendency to form -1 charges. So the rest of those elements in that family, right, that would be this family right there, okay, fluorine, chlorine, bromine, iodine, all right, all of those tend to form -1 charges when they're forming ions, okay, and so that's why. So that's why if you're also, going back to when we talked about alkaline earth metals, they form +2, 3A forms +3. Well, 7A tends to form -1 because it's trying to go this direction instead of, these ones are going backwards to the noble gases. And the ones over here are moving forwards. Fluorine, chlorine, bromine form a -1. Oxygen, sulfur, selenium tend to form -2. Nitrogen, -3, right? Carbon can go either direction. It can either lose 4 or gain 4 electrons. So family 4A can kind of swing both directions here, as either gaining a +4 charge or a -4 charge to get to the nearest noble gas.